Hello all, we are Group 9 and our project is an EOG-based alert system for Aphonic ALS patients. Our team is comprised of 5 students. They are Joe Ham, Josh Hahnemann, Arthur Sparrows, myself, Molly Walsh, Tyler Yang, and our advisor, Dr. Dockert. Before we get into this presentation, it is important to define any abbreviations or definitions we may use in this PowerPoint. ALS is amyotrophic lateral sclerosis, and EOG is electrooculography. The term aphonic is defined as the inability to speak. So, what is ALS? ALS is a progressive neurodegenerative disease that affects nerve cells in our brain and spinal cord. With this disease, all voluntary muscles are severely compromised. Caring for a person with ALS is an everyday task that is extremely costly. The current estimated out-of-pocket cost for caring for someone with ALS is around $250,000. Currently, there is no cure for this disease, and the average life expectancy after diagnosis is 2 to 5 years. Due to the rapid progression of this disease, patients require constant care. Now we will have a closer look at the impact of ALS. With this disease, all voluntary muscles are severely compromised, and progression is to the point where they lose the ability to move, eat, breathe, and speak unassisted. With the loss of voluntary movement, patients will be at a high fall risk and ultimately limited to a wheelchair or hospital bed. The loss of voluntary breathing is a driver to incorporate a ventilator into a patient's treatment plan. However, ventilators can cause a new onset of problems. For example, if they are not cleaned properly, they can cause a severe infection in the body. It is also important to note that ventilators do not eliminate emergent needs, and patients can experience fluid buildup in their lungs. Ultimately, the main cause of death for most individuals with ALS will be related to respiratory failure as the disease progresses to the point where they cannot breathe anymore and fail to notify their caretaker. Our device will have 2 users, the patient and their caregiver. It is known that ALS patients require constant monitoring and assistance. However, hospitalization is often not the answer for continuous care due to the financial burden it imposes. Therefore, patients are typically cared for in an at-home setting. These caregivers are essential to a patient's well-being. However, they are typically a spouse or another family member of the patient and are often not medically trained. The caregivers are also responsible for frequent check-ins with the patient to account for any emerging needs. It is preferred to check in every 15 minutes, which is the standard in the hospitals. However, this is extremely taxing for the caregiver and can limit their own personal time. The existing solutions for ALS alert devices can be broken up into 2 categories, call bells and call bell communication hybrids. The call bell typically features a combination of a switch and alarm, and while these are great tools for ALS patients in the early stages of the disease, they are more limited as the disease progresses. This is due to the fact that call bells typically require some form of voluntary muscle control to operate. The hybrid devices feature an eye-tracking software, and while they do not require voluntary muscle movement, they do require a large cognitive load to operate. Patients in the later stage of the disease have been found to have a cognitive decline. Even these hybrid devices are not meeting the needs of late-stage ALS patients. We plan to develop an EOG-based communication device oriented for use on aphonic ALS patients in an at-home care setting. This will allow patients to ask for help when an emergent need arises and will ultimately enhance the communication between caretaker and the patient.
These are the universal constraints. We have our May 2021 deadline, a $1,000 budget, and resources provided through Drexel University. Arrangements for these resources were made to follow COVID protocols. These are the project-specific constraints. Since this is an expansion of a project, the group decided to continue with the use of the Raspberry Pi rather than other computers. The device was constrained to be fixed to the body, therefore any floating parts that must be carried by the user were avoided. In order to keep the use of the device accessible to cognitive decline, calibration, distress signaling, and overall operation of the device was made as simplistic as possible. To keep the device affordable, Raspberry Pis and breadboards were used to their maximum capabilities, and device casing designs were focused to be minimalistic as well. And finally, FDA regulations for Class 2 medical devices were followed. Here are the first of our requirements. Requirement 1A describes sensitivity or the successful trigger of the alarm and detection of distress signals for more than 97% of trials to match or exceed ICU performance. Requirement 1B is that a distress call must be detected within 20 seconds of prompt. Unconsciousness due to cardiac arrest may occur within 20 seconds, therefore an alarm must be generated within the time frame. Requirement 2A and 2B ensure that prolonged device performance does not affect sensitivity nor time to detect distress signals. Although battery life of existing solutions is roughly 8 hours, due to verification constraints, the requirement is reduced to ensure performance post 2 hours of device usage. The following requirements describe sensitivity performance in response to different light conditions. Lighting affects the functioning of not only the retina, but also constrictor and dilator muscles in the eye, which may affect EOG signals. For requirement 3A and 3B, detection sensitivity and time is to be maintained under high lighting or 20,000 lux, and likewise for requirement 4A and 4B under 0 lux. Lastly, requirement 5A is that the distress call must have a greater than 60 decibel output. Requirement 5B is that the distress call is able to be heard from up to 60 feet away in greater than 97% of instances. The 60-foot range was determined based on typical household square footage.
In this section, I will outline the solution we've developed and the decisions we made to come to this conclusion. To start, here's the EOG interfacing with the subject, capable of reading vertical eye movement and feeding back signal through the vibrational watch unit. There's a speaker inside responsible for communicating distress calls to the caretaker. Next, the internal modules. There are two modules that communicate wirelessly. One Raspberry Pi is responsible for signal inputs and processing, the other responsible for outputs as described earlier. Now, I will relate the components to the following signal diagram. We begin on the top left where the patient operator makes a voluntary vertical eye movement in an attempt to signal for distress. The electric signal is processed on the breadboard and received by the Raspberry Pi unit. The Raspberry Pi collects an initial calibration dataset and uses this as a parameter to determine the status of the patient when monitoring them over a 10-second reading frame. If the reading frame signal is sufficiently similar to the calibration dataset's distress signal, the Raspberry Pi will relay a distress signal to the speaker and communicate distress to the caretaker. If not, the device will feed back a scaling vibrational signal to inform the user how close they were to creating the distress call, to improve the patient's sense of control over the device. Here's a table of the 7 major considerations made over the device. I'll quickly run through each of these parameters in the following slides. First, we'll be addressing the parameters that apply to monitoring the patient's eye movements. A vertical orientation of electrodes encompasses the most late-stage ALS patients and reduces discomfort by requiring less electrodes than other configurations. Next, a distress signal will be characterized by rapid vertical pole-to-pole movement to maximize the potential for the distress signal to be distinct from daily tasks. Later, this will be useful for the Fourier domain analysis, explained in the following slides. Here's a brief demonstration of how the device reads voltage signal in the time domain. On the left, we see very little fluctuations as the eye looks straight ahead. On the right, the patient looks up and down at a constant rate, causing fluctuations that are easy to isolate through a two-dimensional Fourier transform. Next, we address parameters regarding the device's internal logic system. During calibration, this device will generate expected biases towards frequencies specific to the physiology of the patient due to variability between biosignals of patients. The calibration is very simple and fast on the patient's end. They simply must look straight ahead for 10 seconds and then create a distress signal, vertical oscillations, for 10 seconds. The remaining calculations are all automated. Next, we have distress thresholding. To create a robust system capable of filtering electrical and mechanical noise, a Fourier transform was chosen to selectively filter and amplify unwanted signals and expected signals, respectively. Furthermore, this device will take on the Fourier transform of a constantly updating 10-second reading frame to compare similarity with the calibration Fourier transform. If the morphology is over 75% similar, the threshold will be exceeded. Next, we have the outbound signals. Our device makes prominent use of an SSH protocol, or a network protocol that depends on Wi-Fi connectivity. This allows the device to control other devices and push data to them, allowing data to be transferred wirelessly. Here's a brief summary of the usage of the SSH protocol. The main unit on the left receives EOG signal and processes it, and then transfers the information to the output Raspberry Pi through SSH. This output device will then create scaling feedback or communicate distress through the speakers. For the signal to notify the caretaker, an audio speaker was deemed most accessible in cases where failure is unacceptable. Finally, we have the feedback signal where the patient may be notified of how close they are to exceeding distress threshold. A vibrational signal was chosen as it's compatible with most late-stage ALS patients and can add a very tangible feeling of operating the device if enough power is provided. Revisiting this picture, this is our prototype in full. The device has all the listed components as discussed prior, and is capable of calibrating and monitoring a patient with great accuracy. The leftmost unit receives and processes EOG data, while the right unit receives this data wirelessly and outputs feedback according to the power of signal. This video is going to be a demonstration of our device's calibration and distress monitoring protocol. In the interest of time, some clips have been time-lapsed. We begin with calibration. Our calibration begins with the collecting of the frequency profile of the eye at rest, staring straight ahead for 10 seconds. The frequency profile is derived through a two-dimensional Fourier transform of the EOG voltage signal in the time domain. Next, our calibration collects the frequency profile of the eyes vertically oscillating. The expected frequency profile varies between subjects to a great extent, necessitating personalized calibration steps to detect distress signals. Here's a visualization of the frequency domain of our neutral gaze recording. An emulated 1 to 20 Hz bandpass filter has been applied to the following datasets to attenuate mechanical and electrical noise. And here's a visualization of the frequency domain of the vertical oscillations. You'll notice that there's a voltage magnitude spike around 2 Hz, indicating that the dominant oscillation speed is around 2 cycles per second. This frequency domain plot is something that we've dubbed the expected frequency profile. It is distress corrected with respect to noise observed in neutral and normalized to the peak value. If the current reading frame resembles this expected profile by 75%, a distress message will be relayed. In the interest of time, this derivation has been simplified, and I would be glad to revisit this during questions and answers. So here's a quick time-lapse demonstration of Molly moving her eyes and not tripping the distress signal because the frequency profile does not sufficiently reflect the expected frequency's morphology. When Molly does attempt to signal distress through consecutive vertical pole-to-pole movement, she is able to do so within seconds of distress prompt.
The patient is in distress and needs attention immediately.
Now we will cover our verification and validation process. Our first experiment was designed to test our device's sensitivity and performance. We did this through a series of monitored trials in which 5 different subjects were prompted to produce a distress signal at random intervals, repeating the process 5 times for each subject. The results of this tests were to be deemed a success if users were able to generate a distress signal within 20 seconds of an alert prompt for greater than or equal to 90% of their trials. For the construction of this protocol, CLSI standard GP10A was referenced. The results of this test showed 100% sensitivity to distress calls, with each alert attempt being recognized by our device within 20 seconds, thus meeting requirements 1A and 1B. Here we have the results from our first experiment with each of the subjects' alert times shown as an average. The y-axis represents our device's reaction time to detect an attempted distress signal, and as you can see, most reaction times were well under our required maximum of 20 seconds. Our second experiment tested our device's performance post-prolonged usage. For this test, the sensitivity protocol outlined for the previous experiment was followed post 2 hours of device runtime. 2 trials were conducted for each of the 3 test subjects, and the resulting detection times were analyzed using a paired t-test against each subject's respective non-longitudinal data. The test success criteria was the result of a p-value greater than or equal to 0.05, as that would prove there to be no significant difference between the data sets. Standards GP10A and IEC 62133 were referenced for this experiment. The results of sensitivity testing following 2 hours of use did not result in a significant change in performance as we expected. However, as we stated previously, we would have liked to test the device's integrity over a longer period of time, as 2 hours does not reflect a practical time period in a clinical setting. Here we have the results from our longitudinal test, shown in orange. When compared to the non-longitudinal data shown in blue, there was no significant decrease in functionality. Device reaction times for 3 subjects following the 2-hour runtime resulted in an average of 11.15 seconds. Our third test was created to test our device's sensitivity in different lighting conditions, as light exposure is known to have an effect on EOG resolution. The first portion of the protocol tested the device's detection sensitivity in bright lighting conditions, and the second tested sensitivity in low light conditions. Data was collected from trials per each of the 3 subjects and was compared respectively against non-longitudinal data through a paired t-test. Here we have a trace of the output from the EOG in high lighting conditions. The green region represents a period of neutral gaze, and the red represents a period where the subject was attempting a distress signal. The yellow portion is the time after the distress call was recognized. This reading was taken at a lux level around 20,000 lux, which is about the amount of ambient light you would get from a clear sky in the afternoon. You can see a relatively smooth output at this level, and a short detection time illustrated by the red box. But moving on to the graph at low light, you can see a serious drop in resolution. Fortunately, our device was still able to perform properly and within the 20-second time frame. But as you can see, there was a much longer detection period, which could bring more problems to light in larger sample sets. To summarize our testing results, the high-intensity light sensitivity testing did not result in any significant decrease in sensitivity or response time, and neither did the low light intensity portion of the test, although there was an increase in response time. Here we have the combined data for our 3 subjects' sensitivities in the highlight level condition. The reaction times of the device in this setting was faster than those from the previously shown tests in normal lighting conditions and had an average time of around 7 seconds. The data for the reaction times from the low light setting shows a sizable overall increase in detection time. The average reaction time was almost 4 seconds slower than the normal lighting reaction time average. However, it was still under our 20-second response limit. Our next experiment, experiment 4, was designed to test the decibel rating of the device's speaker at different ranges. A decibel and tape measure were used to perform the protocol, increasing distance from the device in increments of 10 feet until a total of 60 feet away. Our original success criteria required decibel ratings greater than 55 decibels from 60 feet away for all tests. But unfortunately, upon testing the speaker, we found that it was too quiet and was only capable of low decibel readings even when inches away from the sensor. Following this, our group added a second success criteria requiring only that the device be capable audible by a set of 5 subjects from a minimum of 60 feet away. Fortunately, all subjects were able to hear the alert tone from 60 feet away. However, our subjects were all in their early 20s and had a decent hearing range. So results could very likely be different if a larger age range was incorporated in the test.
Based on our verification testing and results, we were able to conclude that our solution met 9 out of 10 requirements, and the only failure was for requirement 5A, for which the decibel output was less than the requirement of 60 decibels. In summary, our EOG module can capture calibration data and monitor patients through a Fourier analysis. The process has been verified to respond to distress signals. Haptic feedback can be controlled through a secondary Raspberry Pi connected to the first through SSH. We are working towards optimizing and testing the connection of the DC motor with the Raspberry Pi to improve signal strength. Our CAD team is working on the breadboard and Raspberry Pi housing with an emphasis on the cooling solutions. And we are working with the Drexel Medicine team and Melissa Brownlee for caretaker feedback on our design as the device continues to be developed. Currently, we have shifted around the verification testing to have the third experiment, EOG performance protocol with respect to lighting, cover requirements 3A, 3B, 4A, and 4B. And experiment 4, the decibel analysis, will cover requirements 5A and 5B. Since requirement 5A failed, we included a compensatory binary audible test to determine whether the participant heard the alarm. For the build, we've introduced the use of a secondary Raspberry Pi to connect to the vibrational feedback circuit, thus removing some of the issues presented when the main EOG device and vibrational motor were connected to the same power source. The team has also made changes to our 3D designs for the breadboard and Raspberry Pi housing, as well as to a watch design intended to interface with the DC motor. For our innovation, the output of our vibrational feedback will be modulated by the user's EOG output. The use of the Fourier analysis in our algorithm makes the possibility of false positives decrease without affecting the sensitivity of the device. For our 3D design, there's development of our DC motor housing in a watch and a development for the housing of the Raspberry Pi and breadboard units. And our solution returns a modicum of control back to the patient. For obstacles, the signal processing was subject to electrical noise, so we applied a relevant digital bandpass from 1 to 50 Hertz. The electrode cups deteriorated through testing and replicant models were not readily available, which required us to change through several rounds of electrodes to achieve the best signal. There was an issue with the feedback signal being weak due to current draw from the breadboard, so an alternate board and controller were used to increase the signal strength and communicate wirelessly. There were assorted software difficulties with interfacing open source packages together. For future revisions, we would like to include a blink monitor, possibly through the use of an EMG, to utilize alternate inputs as a scheme to generate two-dimensional signals for purposes in higher level communication. We want to improve the operational distance and power of the vibrational feedback module, improve upon the decibel analysis for audio output due to the skewed decibel results, and optimize electro-human interface to improve signal-to-background ratios with an emphasis on extended use. For the normal adult who has spoken without difficulty since early childhood, the prospect of being unable to communicate through natural speech is incomprehensible. Efficient communication with colleagues, family, and friends is taken for granted. Given the nature of the American healthcare system, patients with ALS are often forced into home care towards the late stages of ALS. For an otherwise financially and emotionally burdening experience, this device was created to aid caretakers in returning a sense of limited autonomy back to the ALS patients with respect to affordability and ease of use. This project was made possible through the help and assistance of our team's collaborators and funding. We would like to take this moment to express our sincere thanks and gratitude.
Here we will discuss our contributions to the project. My name is Joseph Ham, and my concentration is in biomechanics and human performance engineering. I am actively seeking a position in the research and development department of the orthopedics industry. My main responsibilities for this project were CAD development for the Raspberry Pi and breadboard casing and the DC vibration motor watch, as well as electrode application and optimization. The most challenging problem I faced was attempting to increase the signal to noise ratio by testing different electrodes. Gold cup electrodes that were passed down from the previous senior design group were initially used. 3M EMG electrodes were attempted to be used, however, a strong enough signal could not be produced to be detected. We attempted to solder electrodes with different wires and end connections to reduce noise in the signal. As a result, new gold cup electrodes were ordered and were used for the final prototype. Although noise was not completely eliminated, it was significantly reduced.
My name is Molly Walsh, and my concentration is in biomechanics and human performance. For this project, my responsibilities included being the medical correspondent as well as part of the engineering team. Some of my key accomplishments for this project included keeping an open line of communication with subject matter experts, as well as conducting interviews with caretakers and researching the disease. I also collaborated with Joe on the modeling of the housing unit for the breadboards and Raspberry Pi, as well as the watch-like design of the DC motor. I also collected the footage that was then compiled into our demo video. The most challenging problem I faced on this project was creating the CAD model to house our device. This was a task I took on even though I had limited experience in modeling, but wanted to improve my skills. I was able to overcome this problem by collaborating with Joe, who had additional experience with rendering. We also had a consultation with Professor Wong, and where he was able to provide additional feedback. By resolving this issue, the project is now a bit more refined as well as aesthetically appeasing now that wires are hidden. We are also able to incorporate the dynamic feedback system in the form of a watch. For my next career steps, I plan on continuing working part-time at the company Gyroscope Therapeutics, as well as continuing my search for an R&D position in the field of ophthalmic therapy treatments.
Hello everyone, my name is Tyler Yang and my concentration is in bioinformatics. I was the lead programmer for this project, and I was responsible for signal processing, automation of calibration logic, netcoding communication between devices, and scaling feedback systems logic. The largest issue I ran into was the fact that there is a wide range of electrical, mechanical, and physiological signal noise and variability. That required a dynamic system to reliably isolate distress calls from everyday eye movements. This was resolved through revising my signal processing approach to the frequency domain, with internal corrections for patient physiology and observed noise during the calibration steps. In doing so, this device has a varying systems logic depending on the user's calibration input. Following graduation, I am seeking laboratory work in high-throughput bioinformatics systems, particularly in downstream analyses. I hope to have a career in academic research in the distant future.
My name is Arthur Spiros. My concentration is in neuroengineering, and after graduation, I hope to gain some lab experience related to my field and eventually pursue a master's in neuroscience. My main role in this project was in verification and validation design. I was also responsible for maintaining up-to-date circuit schematics and assisting in our overall circuit design. One concern of mine coming into this project was how my teammates and I would be able to coordinate effectively on something of this scale. Originally, I was less inclined to suggest anything regarding other members' work out of fear that it might cause conflict or slow the process. But over time, I got to know my group mates more and felt comfortable making recommendations. This camaraderie built within our team opened up conversations about new ideas and approaches to problems, and I see it as an integral part of the success of our device.
My name is Josh Harriman, and my concentration is in biomechanics and human performance. My role for this project was mainly associated with the circuitry design and development for the EOG device and dynamic feedback mechanism. I assisted in logistical checks associated with algorithm and correlated graphs. Originally, the DC motor and EOG mechanism were connected to the same power source, being the Raspberry Pi. However, due to this, there was excessive background noise, which made it hard to distinguish between that and the distress signal. To fix this, we implemented a secondary Raspberry Pi and incorporated a motor driver chip to control the DC motor and connect wirelessly to the first Raspberry Pi, removing the excessive background noise. For the future, I plan to pursue a career in the research and development of the orthopedics industry. Thank you. Any questions?